Welcome to Introduction to the Normal Distribution. Well, the normal distribution, we're going to have to get used to playing with this. We're going to see it a lot this semester. And this chapter is pretty much dedicated to it. Several other distributions here also, but this is definitely the key one. So a couple properties of the normal distribution we want to talk about. First one is its shape. Okay, one of the things that you need to notice is that it has this bell shape to it. We'll see how I can do on tracing over the top of it here. But this curve that I'm tracing over the top here, this bell-shaped unimodal symmetric distribution, has some properties to it that we want to make sure that we take advantage of. Okay, first thing I want to mention about it is that this curve extends all the way out to negative infinity in that direction, and the curve extends out this way all the way out to positive infinity. Okay, now there is a function that we can actually enter our calculators or any sort of graphing routine and get it to draw this bell-shaped curve. I'll let you take a look at that in the book, and it's very much an algebra thing at this point. But thing to notice about this curve is that even though it's going all the way to negative infinity and all the way to positive infinity, it's going to stay above the x-axis. It's never going to drop below that. It's one of the properties of being a probability density function. And the other thing we know about it is that the total area underneath this curve, even though it runs all the way from negative infinity to positive infinity, that the total area has got to be equal to 1. Okay, so the area under the curve is equal to 1, or if we think about that in terms of percentages, that's 100%. Okay, all right, a couple other things to notice is that, I'm going to change colors here for you, is that at this point right here, and at this point right here, we have what's called a change in concavity. As we notice is that from this inflection point out to negative infinity, and from this inflection point out to positive infinity, the curve is concave up. But this section in the center here, which I'm tracing right now, between those two, that's concave down. So when we change concavity on any function, this is not unique to the normal curve, we say we have a point of inflection. Now the interesting thing for us, or the purpose behind that, is that we notice that it gives us a drawing aid, is that those positions will be exactly one standard deviation above and below the mean. Now recall from our previous work that we know, since this is a unimodal distribution, that the mean is going to fall smack dab in the middle. Now, quick review, just so you remind yourself of this, okay? This parameter right here, mu, is the population mean, and this parameter right here, sigma, that is the population standard deviation. We're working with population models, therefore we're going to have population parameters associated with it. Okay, keep all that stuff in mind. We'll come back. We're going to use all that information in a bit. Let's keep moving. Let's go take a look at an example here. Let's say that we've got a distribution of the heights of adult men and women according to the National Center for Health Statistics. Okay, so let me put in my x-axis here. It's kind of all of a sudden disappeared on us. And a couple of things that we notice here is that the mean for the men, which is centered right underneath the highest point of its distribution, is at 69.2, and the mean for the women is at 60.3.6, and again it's underneath the height, tallest point of its distribution. Okay, so what we see is that the distribution of the men is shifted slightly to the right of the women, which makes sense. We know on average men are taller than women. Okay, another thing that we notice is what happened to the shapes of these distributions. We see that the standard deviation of the men's distribution is slightly larger than it was for the women's distribution, and correspondingly the distribution is more spread out. It's shorter and squatter, because notice both these distributions have to encompass a total area of 1, and so the shape of the distribution in terms of how tight it is packed around the mean is going to be determined by the standard deviation. Just to remind you, remember that the standard deviation is the average distance away from the mean. So as the average distance away from the mean increases, the more short and squat the normal distribution is going to become. Okay? All right. Now a little bit about notation here. We use this shorthand notation. Mathematicians, as a rule, are kind of a lazy lot, where we start off with the first letter here indicates that we're talking about a normal distribution, and then we put the two parameters in here. We'll put mu by sigma to let people know that this is a normal distribution with mean, mu, and standard deviation sigma. Okay, so for example, let's back up for just a second to make sure you see this. The back here I said the height of the means distribution, the height of the men's distribution's mean was 69.2 and the standard deviation was 2.8. So using this notation we were just talking about, it'd be normal, that gives us the shape, the bell shape, with a mean of 69.2 and a standard deviation of 2.8. Correspondingly for the women, again, it was a normal distribution, but this time the mean was 63.6 and the standard deviation was 2.5. Handy notation, we're going to use that quite a bit. Okay, so how do you find proportions under a normal curve? Now, the textbook says you can do it one of two ways. You can do it using a table, or you can do it using the calculator. We're going to use the calculator exclusively. It's just a way simpler way of doing it, okay? It's a two-step process. Your first step is to draw a picture and shade the area that represents the proportion to be found. At first it'll take you a couple minutes to draw one of these, but it'll get really fast once you've done it for a bit. And you want to always do that. You want to get a good sense of what proportion you're looking for before you run to the calculator and go do the calculation. That way, if you make a mistake with the calculator, you'll have an idea whether or not you really made a mistake or not, okay? Quick thing on the calculator. The calculator uses negative E99 for negative infinity. In other words, as far as the calculator is concerned, negative E99 is equal to negative infinity, and that's because that is the smallest number the calculator can handle, and correspondingly positive E99 is equal to positive infinity. Okay, now just one more thing about this. What this notation means, this is engineering notation is what it's referred to sometimes. When you look at negative E99, that's negative 1 times 10 to the 99th. That's what that means. Where this one here, E99, that corresponds to 1 times 10 to the 99th. So notice that this is a 1 with 99 zeros behind it. That's an awfully large number, and it's the largest number the calculator can handle. Okay, so let's go take a look at an example. So let's pretend that we're working with the models from the National Center for Health Statistics, and the first question is, what percent of males are more than 62.9 inches? Okay, well, to do that, we'll go ahead and build ourselves a new screen here, and the first step that we're told that we're supposed to do back there in my instructions was to draw a relatively nice looking bell curve that represents the model. Okay, so we just draw ourselves a horizontal axis, make a bell-shaped curve, or as close to a turtle shell as you can make there. Label your axes so we know what the axis is, and it doesn't have to be any cleaner than this, believe me. So this is height. Good idea to put units in, so we'll put inches there. And I'll put the male symbol here so that we know that we're talking about the males. And I'm also going to put the model that I'm using. We know it was what? Well, let's go back and take a look, make sure remember it was what? 69.2 inches by 2.8 inches, okay? So 69. I can't even keep my head long enough to get from there to there. So it's what? 69.2 and then 2.8. Okay, there we go. I'll remember it this time. 69.2 inches and then 2.8. Okay, so what that tells us is that the center of this distribution is at 69.2. And then when I come out to about here and to about here, where my points of inflection roughly are, that's about 3 inches up and about 3 inches down. So this is roughly approximately about 66 inches, right? Don't need to be exact. You just need you need a marker here. You just need kind of a relative position indicator, okay? And then right here is roughly, well, for 3 inches up, that's going to be what? Roughly around 72 inches, right? Okay. So like I said, again, those numbers don't need to be exact. They're just there for reference numbers for you. Okay. Now, the question they asked us to mark was, what percent of the males is more than 69.2 inches? Well, I didn't really need to go through all this drawing of the inflection points to figure out this problem, but it's good practice to get into it anyway. But more than 69.2 inches, that's going to be this shaded region right here, isn't it? Okay. So that's what we want to do. You want to get in there and shade that. Now, notationally, what that would look like, what the question's going to say, is what is the proportion of males, which is the variable there is going to be x, that is greater than 69.2 inches. So notationally, make sure you understand what I just wrote there. What this would read as, how you would read this in English, is P, we'll make that for proportion or probability or lots of other names. Proportion of what? Heights. In this case, we know we meant male heights, okay? Greater, put an A in there, than 69.2. Okay? That's how you read that. In English, that's how that would be read. All right? Okay. Hopefully you got that, because I'm going to get rid of that. I need to get that out of my way. I'm just kind of plugging up the works here. Okay? All right. So now, once I've done that, hopefully you can see, without me actually having to go through and use a calculator, although we're going to, that proportion, since this is a symmetric distribution, has got to be equal to 50%, or 0.50. Well, let's actually lead it with a 0.50, which as a percentage would be 50%. As we'll see, typically it's not a bad idea to report it both ways. Your viewing public is typically going to want to see it as a percentage. It's going to make more sense to them. Okay, now that said, we were able to do that one strictly from the graph, but let's go let the calculator do it for us also, just so that we can get a look at it. Okay, now the command that we're going to use in the calculator is the normal Cdf command. I'll show you in a minute how to get that on the calculator, but it's a good idea when you're first learning to how to use this is to actually write it down. Okay, now the normal Cdf command on the calculator needs 3 pieces of information from you. It needs to know what is the left endpoint, it needs to know what is the right endpoint, it needs to know what mu is, and it needs to know what sigma is. And if you give it those 4 pieces of information, it can actually do the calculation for you. Okay, so in our particular case, the normal CDF command is going to be, I'm going to abbreviate it as NCDF so I don't have to write out normal every time. It's going to be NCDF. Let's see, what was my left endpoint here? Well, my left endpoint, that's the 69.2. Okay, so that's 69.2. What was my right endpoint? How far did it go out here? Well, I went out to positive infinity, didn't I, right? So remember our discussion just a second ago about what positive infinity was in the calculator. Positive infinity is going to be E99. And then our mean, well, we know what our mean was. We got that right here, right? That's 69.2 also. And our standard deviation is 2.8. Okay? All right, so let's get the calculator out and let's go ahead and do that calculation. So where does the normal CDF command live? Well, it's a second function above your variables key or your vars key. So if you look right there, you'll see where it says distributions. So you hit second and then go to the distributions menu, and you notice that the second item in the distributions menu is normal CDF. So let's go ahead and select that. Now our left endpoint was 69.2. The comma is directly above your 7. Our right endpoint, take a look above the comma. You see where it says E? Yeah, okay. E, right? Is EE there? That's for the engineering notation, okay? So if I want to put an E99, I hit a second and where the comma is at, and then put in a 99. So that's my positive infinity. Put in another comma, now I got to put in the mean. Put in another comma, and let's put in the standard deviation, which was, if I recall correctly, 2.8. Close out the parentheses, hit an enter, and notice out to 3 places we come out with the exact same answer. There's a little bit of round off area here, so we don't get quite 0.5 out of the calculator, but to 3 places of accuracy, that is 0.5 when you round it off. Okay. All right, let's go do another one of these. Let's go back to our slides here and do another one. Okay, so another one they asked us to do is what is the percent of females that are more than 69.2 inches? Okay, so let's go ahead and do that. I'm going to go ahead and just get rid of all of my drawing from this problem. We'll start with a clean slate here. Okay, so remember, first step is I got to do a drawing. Okay, well, so let's go ahead and make a sketch. There's my sketch of my normal distribution, and again, I want to label it. This is heights. Okay, but this time it's the heights of females. Okay, so I'm going to have to go get the model for females. So let's go back, take a look at what the model for females were. So notice in the model for females, it's 63.6 inches for the mean and a standard deviation of 2.5, and again, normal distribution. So we got 63.6 and 2.5. Okay, so that's what basically you should be writing down. So far, so good. Your homework should be looking just like what I'm doing here. Okay, it's got a mean of 63.6. Got a standard deviation about 2.5. Well, 2.5 is going to take me up to about 66, isn't it? Right? So that's 2.5 plus 3.5 there roughly, yeah, that's going to get me to about 66. So somewhere around there-ish, roughly, is 66. Now again, it's just a point of reference, okay? So if I go down 2.5, then that's going to get me to about what? Well, let's see, about 61 roughly, right? Okay, does that make sense? Hopefully it does. So it's kind of in the neighborhood. I don't have to get exact again, just so I have some points of reference, okay? Now let's see, what was the question they wanted to know? What percent of females, are above 69.2? Okay, now here's the thing, why we did these points is this distance, let me get a different color here for you. This distance from there to there, that was one standard deviation, okay? So let's move another standard deviation up. And if we go up another 2.5 inches, that's going to get us to 68.5, isn't it, right? So that point right there is at 68.5. So notice the value I'm looking to mark on my drawing is 69.2. So 69.2, well, where is that? That's out like right around here-ish, isn't it, right? So I'm looking to shade just this little teeny area up here. So let me get rid of this other number because I just getting it. Whoops, we'll grab the wrong thing there. Houston, we got an issue. Yep. There we go. It's not going to let me get rid of that 6. All right, there you go. Okay. Okay, so I want to put in the right number there. That's my 69.2. Right there, and I want to know what that area to the right of 69.2 is. So in our language that we were just talking about in the previous problem, what I'm asking for is to find out what is the proportion of, let's try that again, hold down the shift key. What is our proportion of x's that are greater than 69.2 now in the females distribution? That's what we're looking for, okay? Now I can't do that one by guessing this time. There's no way I can just get it by looking at it. I can come up with a rough idea. It's going to be small. I would say like less than 1%, okay? So kind of in the guess, I'd say less than 1%, but let's go right to part 2 and not have to guess, and let's get the value out of our calculator. Okay, so on part 2 here, I'm going to go, okay, I know what I'm looking for. This is Cdf. My left endpoint is 69.2. My right endpoint is E99. My mean is 63.6. And my standard deviation is 2.5. Notice I got to use the mean and the standard deviation from the model that I'm working in, okay? All right, so let's go ahead and get the calculator up here. Go second vars, number 2 for normal CDF. Let's see, and our left endpoint again was 69.2. Our right endpoint was E99. Our mean was, let's see, what was the mean again? That was 63.6, right? And our standard deviation was, if I believe correctly, was 2.5, but let's check, and it's 2.5, right? Okay, close out the parenthesis, hit an enter, and sure enough, it's about 1%. It's 1.3% basically is what we'd come up with, okay? So what that tells us, back at the ranch here, is that this is equal to 0.013, or if we wanted to write that as a percentage, that's 1.3%. So what that tells us is that, less than 2% of the females are taller than the average height of a male, okay? All right, now I'm going to let you do the last one, and what I'd like you to figure out on your own, see if you can do this, is what percent of males are less than 63.6 inches. And I'll start off the next LDI with that, and you can see if you got it right. Okay, I'll see you back here for the next LDI. Start doing the reading, make sure you're getting up on what's going on with the normal distribution, and we'll talk again soon.